Memory in a computer is like a large array of boxes, called bytes, each with its own address. This analogy is fundamental when understanding how computers manage memory. Each byte can be filled with data, code, or anything that the computer processes. To visualize it, think of memory as a long line of boxes, each labeled with a unique number, enabling the CPU to efficiently locate and retrieve information. When a program runs, it relies on the operating system to manage these boxes, ensuring that the right bytes are accessed at the right time. Now, let's explore how the central processing unit, or CPU, interacts with this memory. The CPU fetches instructions from the memory to execute programs. These instructions may require data to be read from specific bytes or result outputs that need to be stored back into memory. It's important to note that the CPU cannot directly access data stored on the disk. Instead, the CPU communicates only with memory and some special registers. The speed at which the CPU can access memory plays a critical role in system performance. Although registers within the CPU allow for incredibly fast access, taking just one clock cycle, main memory, often referred to as RAM, is relatively slower. This discrepancy has led to the invention of cache memory, a small and fast type of memory located in the CPU itself. By storing the most frequently accessed data in this cache, the CPU can significantly reduce the time it takes to retrieve essential information during computations. To enhance the efficiency of memory management, computers employ a technique known as memory protection. This mechanism ensures that individual programs operate in their own designated memory space, preventing them from interfering with one another or with the operating system. The boundaries of each program's memory access are defined using two special registers called the base register and the limit register. The base register indicates the starting memory address allocated to a program, while the limit register specifies the maximum size that the memory block can occupy. If a program tries to access memory outside its designated range, the system will halt its operation and raise an error, maintaining stability within the entire system. The responsibility of controlling memory allocation rests primarily with the operating system. The operating system not only sets the base and limit registers for each process, but also has complete access to all user and system memory. This access is crucial for smoothly switching between different running programs and addressing any errors that may arise. When a program is ready to execute, it begins as a file on the disk. However, to execute, it must first be loaded into the computer's memory, a process called address binding. Address binding assigns specific memory addresses to both the program's instructions and the data it will use. There are three primary types of address binding: compile time binding, load time binding, and execution time binding. With compile time binding, if the program's memory location is known in advance, the compiler generates code that reflects this specific address. Conversely, load time binding allows for flexibility when the program may be relocated in memory. This flexibility is crucial because programs can be loaded into varying memory locations without the need for recompilation. Lastly, execution time binding provides the most dynamism, permitting programs to be moved at any point as they run. Understanding logical versus physical address space is another critical component of memory management. The logical address is generated by the CPU and acts like a virtual address that a program uses to refer to memory locations. In contrast, the physical address reflects the actual memory location in the hardware. This distinction is managed by a specialized component known as the Memory Management Unit, MMU, which handles address translation and enables seamless interaction between a program's logical addresses and the computer's physical memory. Dynamic loading is a technique that further optimizes memory usage. Rather than loading an entire program into memory, dynamic loading allows for only the portions needed for immediate execution to be loaded. If additional functionality is required later, such as a specific function not yet loaded, it can be retrieved as needed. This method proves particularly beneficial for large programs as it conserves memory and enhances performance. Dynamic linking is another vital aspect of efficient memory management. In contrast to static linking, where all required code is included at compile time, dynamic linking involves linking to libraries at runtime. If a specific library is already in memory, the program can use it directly. If not, the library is loaded on demand. This process not only reduces memory usage by allowing shared access among multiple programs, but also facilitates easier updates, since all programs relying on a library will utilize the latest version without necessitating recompilation. However, memory management isn't without its challenges. One prevalent issue is fragmentation. There are two types: external fragmentation, when free memory is scattered throughout, preventing allocation for new processes, and internal fragmentation, where allocated memory exceeds what's required. Techniques such as compaction can help address external fragmentation by consolidating free spaces, while paging and segmentation techniques minimize wasted space in memory allocation. Paging divides memory into equal-sized blocks, known as pages and frames, which can be loaded independently. By allowing non-contiguous storage of logical memory, paging minimizes external fragmentation issues. Each time a process runs, its pages are loaded into available frames, enabling programs to outgrow physical memory limitations. The central processing unit generates addresses specifically designed for this system, splitting them into a page number and an offset, corresponding to physical addresses promptly. As we delve deeper into context switching, where the CPU toggles between different processes, it's essential to recognize the impact on system performance. In systems utilizing paging, the management of logical addresses and their mappings to physical addresses requires careful coordination. This process, though efficient, can introduce delays, necessitating robust operating system design to ensure optimal resource management. Moreover, the use of specialized hardware components, such as the translation look-aside buffer, TLB, enhances the translation process. The TLB caches commonly accessed entries from the page table, expediting address lookups. A high TLB hit ratio, indicating successful hits on cached entries, can dramatically uplift performance, while lower ratios can lead to sluggish memory access. In summary, memory management is an intricate system of processes and technologies designed to coordinate and control how data is accessed and stored. From the organization of bytes into addresses to the dynamic allocation of spaces for running programs, understanding these concepts provides insight into how computers operate efficiently. The collaboration between the CPU and operating system is vital in ensuring that memory is used effectively, and recognition of issues like fragmentation can lead to innovative solutions that enhance overall performance. Through memory management, we unlock the potential of computing devices, enabling them to run various applications seamlessly and efficiently. When a program is ready to run, it first exists as a file on a disk, typically in a binary format. The journey of this program from a static file on a disk to a dynamic process in memory involves a crucial step known as address binding. Address binding refers to the process of assigning memory addresses to the program's instructions and data, allowing the operating system to manage the memory effectively while the program is executed. Understanding how address binding works is fundamental to grasping how operating systems utilize memory and manage processes. Once a program is loaded into memory, it transforms from a simple file into what we call a process. Before diving deeper into the intricacies of address binding, let's recognize the significance of moving a program from disk to the main memory. This relocation is necessary because the central processing unit, CPU, cannot execute instructions directly from the disk. It operates on data and instructions that reside in memory. The operating system plays a crucial role in this process, managing the finite resource of memory in an efficient manner. There are various stages of address binding that occur at different times, and they can significantly impact how and when memory addresses are assigned to a program. The first kind of binding is what we call compile time binding. In this scenario, if the program's memory address is known in advance, typically at the time of compilation, the compiler assigns specific memory addresses to the program's instructions. This means that the program is generated with a fixed starting point determined at compile time. While this method is straightforward, it poses a limitation. If the program needs to be relocated in memory for any reason, the entire program would need to be recompiled. Next, we have load time binding. This method is used when the program's starting address is not known until the program is actually loaded into memory. In this case, the program is compiled using relocatable code, which allows it to occupy different locations in memory without requiring recompilation. When the program is loaded, the operating system determines the actual address in memory and modifies the addresses in the code accordingly. This flexibility allows the program to be moved around in memory, making it a more dynamic solution compared to compile time binding. Finally, there is execution time binding, which occurs when the program is already running. This most flexible method allows the operating system to relocate processes while they are executing. Special hardware support is required for this type of binding, as the operating system can change the physical memory address of a process while it is executing without halting the program. This feature can optimize memory usage and improve the performance of the overall system. In understanding address binding, it's important to differentiate between logical addresses and physical addresses. The logical address is what the CPU generates when a program runs. It's akin to a virtual address that programs use to refer to memory locations. On the other hand, the physical address is the actual memory address in the hardware where the data is stored. The distinction is paramount. When programs generate logical addresses, they don't directly correspond to physical memory addresses. This mapping is effectively managed by a component called the Memory Management Unit, MMU. The MMU translates logical addresses to physical addresses, and this mapping occurs dynamically at runtime. When a program generates a logical address, it does so to access memory for instructions or data. Still, the MMU takes care of converting that request into a physical address that points to the actual memory location. The user program is entirely unaware of the physical addresses. It only operates with logical addresses, while the MMU and the operating system maintain the cohesion of these address spaces. Dynamic loading further enhances the efficiency of memory usage. Traditionally, an entire program must be loaded into memory for execution. However, dynamic loading allows only the necessary portions of a program to be loaded. This is particularly beneficial when dealing with large programs, since it prevents the system from unnecessarily consuming memory. If a function is called that has not yet been loaded, the operating system can load it at that time, ensuring memory is only used when needed. This leads to more efficient memory management, especially for larger applications, which may contain rarely used components. Another significant aspect worth mentioning is dynamic linking and shared libraries. In traditional static linking, the program includes all the necessary code, such as library routines, during the linking phase before execution. This can lead to larger program sizes, as identical library routines are included in every executable. In dynamic linking, however, the required library routines are linked during program execution. This means that if multiple programs require the same library, they can share the same copy in memory, leading to better memory utilization. Moreover, with advancements in operating systems, updating a shared library also allows all programs using that library to automatically utilize the new version without needing recompilation. This dynamic approach to linking not only optimizes memory usage, but also streamlines the update process, ensuring that applications leverage the latest enhancements and fixes without extensive manual intervention. As processes utilize memory, understanding swapping is another critical aspect of memory management. Swapping refers to the process of temporarily moving a program residing in memory to a backing store, usually a disk, to free up space for other processes. When the operating system needs to load a new process and there is not enough physical memory to accommodate it, one or more processes can be swapped out. The system can then load the required process into memory. This process is akin to managing items in a storage room, moving things in and out to make space for new arrivals. Finally, it's essential to address the challenges faced in dynamic memory management and swapping. A program must be idle before it can be swapped out. If it's actively waiting for input-output operations, swapping might produce errors and lead to data being lost or misplaced. Modern operating systems are built to handle challenges like these by implementing more sophisticated algorithms that prioritize which processes to swap out based on their activity and memory usage patterns. Understanding address binding and execution time management is critical in forming the foundation of how operating systems function. The way processes are managed in memory how memory addresses are assigned and translated, and how optimization techniques like dynamic loading and linking are handled significantly influence application performance and resource management. This intimate knowledge of memory management gives students insights into the intricacies of operating systems, encouraging a deep dive into their mechanisms to enhance application performance and memory efficiency. Paging is a memory management method that divides memory into small, fixed-size blocks called frames and pages that are loaded into memory as needed. This approach is fundamental in modern operating systems and helps optimize the usage of memory in a more efficient manner. When a computer program runs, it doesn't necessarily need to have all of its data in memory at once. With paging, only the necessary pages are loaded, enabling the execution of larger programs than what physical memory would typically allow. This feature provides crucial benefits over older memory management techniques, such as avoiding external fragmentation and enhancing the way programs use memory. Let's explore the fundamental aspects of paging. Imagine your computer's memory as a series of tiny compartments, each capable of holding a fixed amount of data. These compartments are known as frames in physical memory and pages in logical memory. When a process executes, the pages of that process are allocated to the available memory frames. Because both frames and pages are of a uniform size, this arrangement simplifies memory management. It prevents the fragmentation issue encountered in systems without paging, where free memory spaces become too small to accommodate new processes, despite having an adequate total amount of memory available. When it comes to how these addresses are handled, this is where the concept of address translation comes into the picture. Each time a process generates an address, it consists of two components, a page number and an offset. The page number identifies which page the CPU is working with, while the offset denotes the exact location within that page. The operating system and hardware collaborate closely to translate these logical addresses into physical addresses in memory, utilizing a page table that records the mapping of page numbers to their corresponding frames in physical memory. This process might seem trivial, but it is essential for the smooth running of processes in our computers. Despite its advantages, paging is not without its complications. Although it skillfully sidesteps external fragmentation issues, it can still encounter internal fragmentation. Internal fragmentation occurs when a page is only partially filled with valid data, leading to wasted memory within that page. For instance, if the last page allocated contains only a small amount of information, the remaining space in that page goes unused. Thus, while larger page sizes may increase the risk of internal fragmentation, smaller page sizes can introduce excess overhead and diminish the efficiency of disk I/O operations. The choice of page sizes is therefore critical. Generally, page sizes range from 4 KB to 8 KB, with some systems opting for larger sizes. Each operating system carefully considers this size to strike a balance between minimizing fragmentation and enhancing overall memory usage efficiency. This determination significantly impacts memory management, data transfer speeds, and the performance of various applications. Next, we need to look into the role of the operating system more closely. Operating systems are responsible for tracking the allocation of pages in memory through structures like the frame table. This table keeps a record of which frames are occupied or free, ensuring optimal utilization of memory resources. When a program demands a particular page, the operating system retrieves it from the backing store, a place where data is temporarily held when it is not actively in use, and loads it into a free memory frame. As processes are started, the operating system first assesses their memory requirements and assigns available frames accordingly. Each page of the newly running process is placed into one of these frames, and corresponding updates are made to the page table to reflect which frames contain which pages of the process. As we venture deeper into this subject, it's crucial to consider context switching. In environments employing paging, there's an essential separation between the programmer's perceived view of memory and the actual physical memory layout. When a process is loaded and running, its logical addresses get mapped to physical addresses via the operating system's page table. However, when a process is swapped out of the CPU, updating this mapping requires time, potentially introducing delays and negatively influencing overall system performance. The technical nuance discussed above highlights the intricacies of managing memory effectively in modern computer systems. The efficiency of page tables and the methods in which they are managed are pivotal to maintaining a responsive and speedy computing experience. On a hardware level, operating systems must implement page tables in such a way that ensures seamless transitions between different processes and minimizes the overhead associated with memory access. A key innovation designed to alleviate delays during memory access is the Translation Look-Aside Buffer, or TLB. The TLB acts as a high-speed cache, storing a small number of page table entries for rapid access. When the CPU files a request for memory access, it checks the TLB first for a quick response. If it finds the required entry, a TLB hit, the translation is brisk. However, if the entry is not found, a TLB miss, the system must traverse the page table in memory, incurring a performance penalty. In essence, the effectiveness of paging hinges on a delicate balance between the hardware's need for speed and the operational requirements of the operating system. The design of the TLB and the structure of page tables influence how effectively an operating system can manage memory, prompting a review of various architectures used to optimize memory management, such as hierarchical paging or inverted page tables. Ultimately, paging is a powerful and effective strategy for managing memory. Its design allows systems to maximize their available resources, run larger applications, and maintain performance reliability. The concepts of logical versus physical addresses, page tables, and the importance of the TLB are foundational to understanding this critical component of computer architecture. By examining the nuances of paging, we gain insight not only into how modern operating systems function, but also into the fundamental principles of memory management that underpin the efficiency and effectiveness of computing today. Swapping is the process of temporarily moving a program or process out of the computer's memory to free up space and then bringing it back when it's ready to continue running. This mechanism is crucial for ensuring that a system can run more programs than the physical memory, or RAM, can hold at one time. Think of it like reorganizing your closet. When you want to add a new piece of clothing, you might take something out to make space. Swapping plays a similar role in computer memory management by allowing operating systems to maximize resource utilization and improve the overall performance of the system. In the context of computer systems, swapping helps maintain performance, especially when many applications are running concurrently. When a process is moved from RAM into a backing store, often a disk, it frees up space, allowing the CPU to load another process. This effective memory management technique can be likened to a juggler who seamlessly transitions between different objects, ensuring that each object is kept in motion while others are temporarily set aside. Standard swapping typically involves transferring processes between the computer's main memory and a storage area known as the backing store. This backing store must be large enough to hold entire process copies. When the CPU wishes to execute a process, it first checks if that process resides in memory. If it does not, the system must swap another process out to make room. The required process is then loaded back into memory, where it can continue execution. To illustrate this, let's consider a swap time example. If a process is 100 megabytes in size and the system's transfer speed is 50 megabytes per second, it will take approximately 2 seconds to swap that process in or out. However, a larger process, say 3 gigabytes, would take around 60 seconds for the same operation. Thus, processing larger data files can significantly affect swap times and overall performance, highlighting the importance of efficient resource management within an operating system. Now, swapping can be optimized. Instead of exchanging entire processes, operating systems can focus on swapping parts that are actively being utilized. This selective swapping is more efficient as it minimizes the required transfer time and maximizes memory usage. When processes need to update their memory needs, they must communicate these changes back to the operating system, so the memory manager can make informed decisions about what to swap out and what to keep. However, there are challenges to manage in the swapping process. For example, a process has to be idle, meaning it cannot be performing input-output I/O operations at the time of swapping. If the system attempts to swap out a process that is waiting for I/O completion, it could lead to issues, such as data being misplaced in memory. It is crucial for operating systems to implement safeguards that prevent the swapping of processes with pending I/O, often by utilizing special buffers to ensure that data is correctly managed during transitions. In modern computing systems, traditional swapping techniques are not as prevalent due to their inherent inefficiencies. With advancements in technology, operating systems such as Unix, Linux, and Windows have developed various swapping strategies. For instance, these systems may implement swapping only under conditions where free memory is low, or may utilize techniques that allow for partial process swaps, where only parts of a process are moved in and out of memory. Mobile operating systems, such as those found on smartphones and tablets, approach swapping differently due to the variations in hardware and resource limitations. Traditional swapping isn't a viable option here, since mobile devices typically use slower flash memory instead of hard disks, and available storage is more constrained. For example, under low memory conditions, iOS prompts apps to relinquish unused data, keeping only critical operations in memory. Android approaches the issue similarly, opting to pause applications consuming excessive memory while preserving their state for quick resumption later. The concept of swapping ties in closely with other memory management strategies, such as paging and segmentation, which also aim to manage memory more effectively. Paging, for instance, involves dividing memory into fixed-size blocks called pages, which can be filled as needed. Segmentation, on the other hand, organizes memory into segments based on the logical structure of a program, creating a more intuitive memory management system that reflects the programmer's view of data and code organization. Memory management is an essential aspect of operating systems, ensuring efficient process execution and resource utilization. Through swapping, paging, and segmentation, operating systems can enhance performance, prevent bottlenecks, and facilitate a seamless multitasking environment. As application demands grow and memory requirements become more complex, the role of these techniques becomes increasingly vital in maintaining effective computing performance. In summary, swapping is a powerful memory management technique that allows systems to effectively juggle multiple processes by prioritizing memory use. By temporarily moving processes out of memory, systems can ensure smoother operation, improved performance, and more efficient utilization of available resources. Understanding the dynamics of swapping, combined with other memory management strategies, is crucial for anyone aspiring to navigate the complexities of modern computing environments effectively. As we continue to explore these ideas, we recognize that memory management is more than just a technical necessity. It's at the heart of the effective functioning of our computer systems, enabling them to meet the demands of today's fast-paced digital world.